You gotta get the establishing shots.
It's all B-roll, baby.
Yeah, baby.
From Alibaba, and then bringing it to like a local merchant so that they can craft it and you're still like supporting a local economy. It's like more ethical in both directions. A secondhand, like vintage, like kind of like a fur, you know? Spoilers. That's such a great graphic.
Yes. Okay, so we're all set, right?
Yes.
Okay.
To be or not to be?
That is the question.
No, she has to have something. She has to have like a reward.
Do you want me?
Yes. I mean, I assumed.
Honor to be able to introduce Swethas to giving her doctoral thesis presentation. She's been a member of our family for a number of years, starting with COVID. I use the word family because it really has been like a family in our lab, and she's been really a dear and treasured member of that family. If there are two parents fighting for the other one, don't use any special words here, we're not use librarians. But really has been a pleasure working, having her in our family, working with her, and with Pradeep, and Pradeep working with her, and her working with both of us. She's done some really exciting stuff. As we'll find out, she's the only person I know probably in the world who's made 9 different drugs against tuberculosis, designed it on her own. It's pretty damn good. I really have been eager to see her move on and go into the next stage of her career, although with some sadness. Now that I see that she's actually engendered probably the biggest turnout we've ever had in this room for a speaker, plus the 17 online, I'm thinking maybe we do have to keep her for a couple more years. So thesis committee, keep that in mind. But with all seriousness, she's already looking at her watch, so she's a lot to tell you. So I'm just going to welcome you here, and I hope you can enjoy her talk.
My watch was actually telling me I needed to relax. Alright, thank you everyone for coming today. I'm going to be telling you about a project that I've been working on for the past few years, where we studied anhydrolysis in Mycobacterium tuberculosis to develop new pyrazinoic acid prodrugs that are effective in the treatment of pyrazinamide-resistant tuberculosis. So we're studying TB because it's a major global health burden. It's an infectious disease that presents with general symptoms such as fever, cough, and chest pain, and it's caused by this bacteria, Mycobacterium tuberculosis. So MTB infects 1/4 of the world's population, and it's responsible for over 10 million new cases each year and over 1 million deaths per year. Now, this morbidity and mortality that we see exists even though we have a curative regimen. So there's currently 2 first-line regimens for the treatment of TB. One is a 6-month regimen that involves the use of rifampicin, ethambutol, isoniazid, and pyrazinamide. And the second is a newer 4-month regimen that also includes isoniazid and pyrazinamide, but replaces rifampicin and ethambutol with high-dose rifapentine and moxifloxacin. However, drug resistance is a major problem in TB. So we have multi-drug resistant TB, or MDR-TB, which is resistant to rifampicin and isoniazid. And then we have XDR-TB, or extensively drug-resistant TB, which in addition to these 2 is also resistant to the second-line fluoroquinolines and either linezolid, bedaquiline, or the second-line injectable drugs. Now, because of this drug resistance, we have to be constantly coming up with new anti-tubercular agents. However, we see this relative stasis in drug development in TB. So we can see here that many of the clinically used agents were discovered in the 1950s and the 1960s. But since 2000, there's only been 3 new agents approved for the treatment of TB. And part of the reason that it's so difficult to make new TB drugs is because of MTB's cell wall. So MTB has this complex and lipophilic cell wall that has these characteristic glycolic acids. And this cell wall really prevents the entry of many standard antibiotics that can work against other bacteria. One strategy for getting drugs into MTB is to use prodrugs, which are able to enter the cell and then are biotransformed into their active form. And I'm going to highlight here pyrazinamide because it's a very important antitubercular. It's in both of the first-line regimens, and it has this unique sterilizing activity that's effective against non-replicating persister populations of MTB. It's the antitubercular that allowed us to shorten TB therapy from 12 to 6 months and significantly lower relapse rates. And because of these key features, it's the most commonly retained drug in newly proposed regimens. Now, despite its central role in treating TB, it's not totally understood how PZA works. There's thought to be maybe more than one mechanism of action and a few different theories. One is that PZA acidifies the inside of the bacterium. Another is that it inhibits fatty acids synthase 1. A third is that it inhibits RPSA, thereby inhibiting translation. And a fourth is that it inhibits PAN-D, thereby inhibiting pantothenoate synthesis. And I want to highlight this last mechanism of action here because recently there's been really accumulating evidence suggesting that PAN-D is really a target of PZA. Now, what all of these models share is that PZA enters the bacterium and is activated by this non-essential amidase, PNCA, into the active antitubercular moiety, POA. And so what I really want you guys to take away from this slide is that PAN-D is a target of PZA, PNCA activates PZA into the active form POA, and that POA itself is much less effective against treating TB in animal models. So as I mentioned, PZA is activated by this non-essential amidase, PNCA, and because of this non-essentiality, we see that 95% of clinical resistance is due to loss of function mutations in the gene that encodes PNCA. And this is a major problem. We now see that 60% of MDR TB is also resistant to PZA, which really complicates treatment and prevents the use of both of the first-line antitubercular agents and threatens short-course therapy. Now, this mechanism of activation of pyrazinamide by PNCA is analogous to the mechanism of activation of this compound, DG160, which was studied by Carly Levine, a former graduate student in our lab, and Pradeep Kumar, who's a professor in our lab. And Carly found that DG160 is activated by the non-essential amidase AMEC to release isoquinoline-1-amine and the active acid, fusidic acid. And she found that when she measured the drug potency in MTB by measuring the MIC, which is a measure of the concentration needed to inhibit bacterial growth, she saw potent activity in wild type indicated by a lower MIC, but when she interrupted MEC activity with a transposon insertion, she saw that the MIC increased to 12.5 and 25 to 25, indicating a loss of drug activity. Carly also saw that when she treated with fusidic acid or isoquinoline-1-amine alone, you also saw a loss of drug potency. And this really told her that this parent structure of DG160 is needed for activity, and that activation by MEC is also important. Carly also showed that in an MEC frameshift mutant, DG160 was metabolized much slower. leading to a higher MIC. And she also showed that when she overexpressed MAC, there was a more rapid metabolism of DG160 and a lower MIC. Now, in addition to DG160, Carly also saw that the antituberculars DA60 and DG85 were activated in MTB by the same amidase, MAC. And then independently, Cliff Berry's group saw that this indole 4 carboxamide structure enters MTB, is hydrolyzed by MAC to release this active amine, which then goes on to inhibit tryptophan synthesis. So what we're seeing here is that many of these amide antituberculars appear to be undergoing amide hydrolysis in MTB, and that MAC, this one amidase, is capable of hydrolyzing several different antituberculars. Paridi Sukeja, another former graduate student in our lab, studied this compound DG77, and she saw something similar in MTB. She saw that it was it underwent amide hydrolysis to release its active compounds, and when she did TNC, she found that transposon insertion into several amidases led to increased bacterial fitness under drug treatment. And this, now this work is still being validated, but it suggests that several amidases may be able to activate the same compound. Now, Carly wondered if she could learn from what she was seeing with DG160's metabolism by MAC to get POA release within MTB via MAC rather than PNCA. So what she did was conjugate POA to isoquinoline 1-amine to get this parent structure, JSF4302, and she found that POA was indeed released within MTB and had a MIC better than PCA. And then Courtney Eldrick's group similarly explored this idea by creating this cephalosporin POA conjugate, which they found released POA within MTB via the beta-lactamase BLOS-C. However, their parent compound actually had more potent activity in a BLOS-C mutant compared to wild type, suggesting that this compound's activity may actually be due more to the cephalosporin or the parent compound than POA release. Both of these compounds had suboptimal PK or pharmacokinetic stability in mice or in model organisms, so we didn't pursue further studies with JSF4302. But importantly, they demonstrated that both of them can release POA within the mycobacterium via amidases or enzymes other than PNCA. And this is really important because if you guys remember, most PCA resistance is due to mutations in the gene that encodes PNCA. So you can now get POA release in PCA-resistant disease. So to summarize what we're seeing here so far, we have this general structure within an antitubercular, the amide bond, and we're seeing that amidases within MTB can release a carboxylic acid, which from here on forward will be highlighted in black, and an amine, which here on forward will be highlighted in red. And Carly saw that MEC can metabolize a lot of these compounds. Cliff Berry's group also found the same for their compound, and then Paridi showed that DG77 also undergoes amide hydrolysis. Carly then applied this idea to create a prodrug, but however, this prodrug had poor PK. So what we wondered is whether we could expand on this idea that Carly started to create this prodrug by further studying amidases and how they metabolize amides within MTB, and to start to generate more prodrug structures. So we asked 3 questions. How many MTB amidases are there, and how prevalent are amide antituberculars within known antitubercular libraries? What are the amide antituberculars that undergo amide hydrolysis inside MTB? And can we use the carboxylic acid and amine metabolites that are released by amide antituberculars as sort of building blocks to rapidly design many new prodrugs? So I first took a look at how many MTB amidases there are, and identified 155 known and putative amidases, the majority of which are non-essential and have a wide range of functions within MTB. I then looked at known antitubercular libraries. So we have 2 of these libraries in our lab. The first one I looked at was the GSK, or GlaxoSmithKline library. GSK screened 2 million compounds, and they screened for potent antitubercular activity as well as drug-like characteristics, and published 177 hits. And of these 177 hits, we found that 64 of them, or over a third, had amide bonds within them. I then took a look at the TB Alliance, or TBA library of compounds. This is a library that's really a consolidation of many drug discovery efforts. And we found that 557 of over 1,300 antituberculars had amide bonds. So in total, that left us with 621 amide drugs in our lab that we could study. And we also found that just over 40% of all these antituberculars in known libraries in known antitubercular libraries had amide bonds, suggesting that this is a structure, a common structure in compounds that have successful anti-MTB activity. So we next asked which of these amide antituberculars undergo amide hydrolysis inside MTB. And to do this, because testing 600 compounds is a lot, we decided to develop a pooled screening approach for detecting amide hydrolysis that's based on the interbacterial metabolism protocol developed in Joel Freundlich's lab. And this approach was developed with Matt Zimmerman, Farak Kaya, and their team at Hackensack Meridian Health. So what we did is we pulled 8 to 12 drugs in a single culture of MTB, and at 0, 1, and 24 hours, we used LCMS to quantify metabolism of the parent compound and detection of the downstream amine and carboxylic. To validate this approach, we pooled 13 drugs at 10 micromolars each, 1 micromolar each, and then compared these pools to individual incubations at 10 micromolar. And we found that for the most part, our 10 micromolar pools recapitulated what we're seeing in our individual incubations, but there was some signal loss at the 1 micromolar pools, so we moved forward with our 10 micromolar pooling approach. And using this experimental design, we screened 533 compounds from the GSK and TBA libraries, and we found that 222, or just over a third of them, were hydrolyzed at the amide bond. Of these 222, we found that 150 had at least 50% metabolism in 24 hours, 109 had at least 80%, and 77 had over 98%. We then started to look at what types of what characteristics these structures have and what types of structures tend to undergo amide hydrolysis in MTB. This is work that we've done in collaboration with Joel Freundlich here at NJMS. And on this plot, you can see that we've mapped structural diversity of the compounds that we screened. The squares here represent compounds that we screened from the TBA library. The circles represent compounds that we screened from the GSK library. And those that are highlighted in dark green are those 150 compounds that were metabolized by at least 50% in 24 hours and had a metabolite detected. And the takeaway from this graph is that the compounds we're finding that undergo amide hydrolysis really have a range of different structures. Also working with Joel, we started to model, using Bayesian modeling. We developed a model that can predict what types of compounds will undergo amide hydrolysis in MTB. And this is a ROC curve that's just based on the first 200 or so compounds that we tested. but we can see that it has a pretty good AUC of around 0.9. And these are still preliminary results, but we're going to expand this to include our entire data set. So we then hypothesized that we could use these carboxylic acid and amine metabolites that are being released in MTB to sort of piece them together and design new amide prodrugs. And we started doing this with POA conjugated to amine because we know that PZA is such an important antitubercular. So to show you guys what I mean here, we have this POA conjugate, which is POA conjugated to an amine, and it could be hydrolyzed by an amidase other than PNCA, releasing POA and PZA in the majority of PZA-resistant strains, therefore restoring intrabacterial POA activity. You can also have a POA conjugate where POA is linked to an active amine, creating a dually active compound. And I think most excitingly is if we could create a POA conjugate that is activated by more than one amidase and releases POA, because then you would need more than one mutation in a single activating enzyme to get total resistance. And just to remind you guys, Carly explored this idea already with JSF42 and showed that she can release POA when it's conjugated to isoquinoline 1 amine, but it had poor PK, so we wanted to expand on this idea and more systematically approach prodrug design to generate many different structures. So here I have graphed the metabolism over time of all of the parent compounds that had a confirmed carboxylic acid or amine metabolite. And we decided to start to conjugate POA with the amines of those compounds that were most extensively metabolized within MTB first. And by doing this, we generated 19 POA conjugates. Here, again, in black is the part of the compound that would become POA, and in red are the amines from those parent structures that were metabolized in MTB. PG79 was unstable when we reconstituted it in DMSO, so we moved forward with studying the remaining 18 compounds. And the first thing that we looked for was POA release in MTB culture. We found that most of our compounds release POA and that they largely have a corresponding decrease in their parent compound over time. And then when we looked for POA release of these compounds in spent media, we saw that there was no POA release due to any degradation in the media or any extracellular enzymes, suggesting that this POA release is intrabacterial. After looking for POA release, we then looked for PZA-like activity in PZA-resistant strains. And we did this by looking at the drug potency in H37RV at a pH of 5.9, because we know that PZA needs an acidic environment for activity. And we found that PZA had an MIC of 200 micromolar. When we looked at our 18 conjugates, we found that 13 of them had an MIC either equivalent to or even better than PZA. We then measured drug potency in a PAN-D mutant. So recall that PAN-D is one of the targets of PZA, and what we would expect is that this PAN-D mutant is resistant to PZA or a compound that acts like PZA. So here for PZA we see a corresponding increase in MIC, and for 11 of our compounds we see that the PAN-D mutant is resistant relative to the wild type strain. We then looked for PZA activity in PZA resistant strains. So again, 95% of clinical resistance to PZA is seen from mutations in PNCA, So we tested our PNCA mutant, which is unable to convert PZA to POA. And again, we can see that it is resistant to PZA as expected, but we found that all 11 of our compounds that had PZA-like activity in the PAN-D mutant retained their activity in the PNCA mutant, suggesting that they are releasing POA via amidases other than PNCA. So here again are the initial 19 structures that we designed, and I'm highlighting the 11 that had PZA-like activity in PZA-resistant strains. So we now have several structures that we can test PK or pharmacokinetic stability in to see if we have improved stability on top of JSF 4302. So we went ahead and looked at plasma stability, at murine plasma stability in vitro. And in black here, you can see JSF 4302. And we see that several of our POA conjugates have improved plasma stability. So I then looked at the PK of those compounds after in vivo in CD1 mice after they were orally administered at 25 milligrams per kilogram. And again, we can see compared to JSF 4302 down here, they had a several-fold improved PK. And by starting to look at the structures of some of these compounds, we can see, we can start to look at the chemotypes that promote murine stability. So, for example, PT260 and PT225 are our most stable compounds, and we can see here that they both have an electron withdrawing group on the meta position of this aromatic ring. So we then look closer at our best compound, PT260. So PT260 released the most POA in 24 hours. It was the most stable in mice, and it had the lowest MIC. Had one of the lowest MICs in wild-type RV, but had PZA-like activity and retained activity in PZA-resistant strain. So we then asked, if not PNCA, what is the mechanism of activation? And because this parent structure is different than PZA, what are the similarities and differences in the mechanism of action between PZA and PT260? So to answer these questions, we used a genome-wide CRISPR-I knockdown approach. This is a screen that was developed in Jeremy Rock's lab at Rockefeller University. And what they did is they created a library that, when induced, will knock down the expression of 98% of the genes in the MTB genome. And when you do this in a given condition compared to a control, you can start to understand the effect of expression inhibition on each gene in a given condition. And so to walk you guys through what this means is, if the condition is drug treatment here, this is from one of the papers published from the Rock Lab, where they screened many of the first and second line antituberculars. And using isoniazid as an example, we can see that knockdown of a drug target, in this case INHA, will lead to increased vulnerability in this screen. And then knockdown of a drug activator, in this case CAT-G, will lead to increased bacterial fitness or survival. Now, they did not screen PZA in their initial paper, so the first thing we did when we were gifted this library from Jeremy Rock was to validate that it was working in our hands. So we screened INH, and we found that our results corresponded to theirs. We then screened PZA and PT260 to compare their mechanisms of activation and their mechanisms of action. And we did this at both an acidic pH, in which we know PZA is active, but since the role of acid in PZA activity is not fully understood, we also did this at a neutral pH of 6.8. So I'm showing here first just those 155 amidases that we identified in MTB. And we can see that for PZA here on the left, that our top hit was PNCA, which makes sense. When you knock down PNCA, you get increased bacterial survival in the presence of PZA. And then for PT260, we identified 7 amidases for which knockdown led to increased survival, and our top hit was very familiar. We see MADC again as a potential activator. We then did sequence homology on the protein sequences of these 155 amidases, and I've highlighted here in purple the hits from the last slide that we got for PT260 as potential activators, and in blue the hits from PZA. And what we see is that MUC clusters together with another hit, AMI-A2, and that these two amidases share the same PFAM domain, suggesting that they may have overlapping activity and that they may both hydrolyze PT260. We then took a look at all of the genes involved in PZA and PT260 activity and resistance. And first highlighting here PAN-D, which is a target of PZA, and RV3603C and PAN-C, which are upstream in the operon of PAN-D, and their knockout would lead to knockout of PAN-D as well. And we can see that PT260 shows a similar pattern for this operon as PZA, in that knockdown of these genes leads to increased vulnerability to the compound. This effect is drug specific, and we didn't see it in the acid alone. Then looked at RPSA. So this was another putative target of PZA, but we see that knockdown of RPSA doesn't seem to affect PZA activity or PT260 activity. And then for fatty acid synthase 1, we see that knockdown of the gene that encodes this actually leads to increased bacterial survival, which is the opposite of what we would expect if it was a drug target. Then I looked at the potential drug activators. So here we can see that knockdown of PNCA increases bacterial fitness in PZA, but not PT260. And then for ME-A2 and ME-C, we see that knockdown does not affect survival in PZA, but that it increases survival in PT260. So to summarize, it appears that both PZA and PT260 target PAN-D, that PZA is activated by PNCA, and that PT260 may be activated by ME-A2 and ME-C. So I'm now showing all of the genes for which knockdown leads to increased vulnerability in acid, PZA, PT260, or some combination of these three. And I'm not going to go into the details here, but what I want to highlight is that knockdown of 44 genes led to increased vulnerability to PT260, but not PZA. And when we did pathway analysis on these genes, we found that they were enriched in oxidative phosphorylation, suggesting that PT260 may have a secondary mechanism that's related to this pathway. But when we looked at genes for which knockdown led to increased vulnerability to PZA, but not PT260, there was only one gene, RB1129C, which is a transcription factor, and this suggests that PT260 activity encompasses PZA activity, and that this activity is largely due to POA. Now these are the knockdowns. These are the genes for which knockdown increased bacterial fitness. For in acid, PZA, PT260, or some combination of those three. And again, I'm not going to go into the details, but when I did pathway analysis on these genes, they were enriched in phosphate uptake and regulation, cell wall biogenesis, fatty acid synthesis or metabolism. So these are pathways that may be involved in resistance to these compounds. And finally, just to really hammer home this point, I'm highlighting that that knockdown of PNCA, increased bacterial fitness in PZA, and that MEC and MEA2 did so for PT260. And we next looked to validate this mechanism of activation using purified enzymes. So in addition to testing PT260 here, we also tested 4 other POA conjugates because they had structural similarity to PT260. And we thought maybe they are also metabolized by MEC and MEA2. And what we can see here is that both PT260 and PT225 release higher levels of POA, that PT598 and JSF4302 release moderate levels of POA, and that PT594, 610, and PZA really don't have much POA release. We then did the same with recombinant PNCA, and we find that POA release only occurred for PZA, again confirming that our POA conjugates have POA release through amidases other than PNCA. Unfortunately, we were unable to purify AMI-A2, and so we're currently constructing AMI-A2 overexpression and knockout strains to understand how AMI-A2 affects PT260 activity. But when we raised drug-resistant mutants to PT260, we found that none of the mutations were in AMI-A2, MEC, or in any other MTB amidase that we had identified, suggesting that the frequency of resistance due to mutations in activating amidases are extremely rare. We also took a look at the frequency of resistance to PT260 in general and found that it was less than 1 times 10 to the minus 7, and this is lower than pyrazinamide and in the range of other antituberculars. And this is work that was done with the help of Alyssa Oki. So after seeing that PT260 activity encompasses PZA activity and MTB, we then went back and looked more closely at the PK in mice, and we took a look at hepatic stability by using mouse liver microsomes, and we found that PT260 had moderate stability in mouse liver microsomes, and that about a third of this metabolism was due to NADPH-dependent CYP enzymes, suggesting that there was not an extensive amount of CYP metabolism, and we also found that there was POA release in these mouse liver microsomes, suggesting that some of this hepatic metabolism is occurring via liver amidases. We then looked at in vivo PK again in CD1 mice, but this time at a higher oral dose of 200 milligrams per kilogram, to see if we could start to reach MIC levels, but unfortunately we see that the concentration in the plasma is still just under our MIC 90 value at 30 minutes and 1 hour. But interestingly, we saw this accumulation in the lung tissue, so we went ahead and looked at its efficacy in mice. But we saw that PT260 did not have any efficacy compared to our vehicle control. So this suggests that we still need to work on further stabilizing on PK stability in a mouse model. But when we looked at plasma stability in rats, beagles, non-human primates, and humans, in addition to mice, we see that PT260 had moderate stability in mice and in rats, but in beagles, non-human primates, and in humans, it was totally stable for at least 4 hours. So our next steps are to do more PK studies in higher mammals. And then finally, we applied this concept of prodrug design that we used for POA to another carboxylic acid. So if you guys remember BG160, the molecule that Carly studied from the introduction, this is a compound that had an MIC of 1.56, was metabolized to release fuchseric acid, the active component in MTB, and isoquinoline 1-amine. But when Carly looked at the drug potency of just fuchseric acid, it had a higher MIC of 100 micromolar. When I conjugated fuchseric acid to the amine from the TBA antitubercular, DT610, to create this fuchseric acid conjugate, FT610, we again found that we could restore drug potency in MTB. So here we think we can apply this concept to several different carboxylic acids or amines and sort of develop a new strategy or platform for designing prodrugs. And then you could even apply this idea to other enzyme substrate duos to create prodrugs that are based around another chemotype as well. So in summary, to our 3 questions that we asked at the start, we found that over 40% of antituberculars in the GSK and TBA libraries had amide bonds in them. When we screened over 500 of them, we found that just over a third underwent amide hydrolysis in MTB culture. We then took the amines from the most rapidly hydrolyzed antituberculars and conjugated them to POA to generate these 19 POA conjugates. We found that 11 of these conjugates had PZA-like activity in PZA-resistant strains. And we then found that our most promising conjugate, PT260, encapsulates PZA activity, is likely activated by more than one non-PNCA amidase, namely MEC and MEA2, has high barriers to resistance, improved PK in mice, and is stable in the plasma of beagles, non-human primates, and humans, making it a candidate for more testing in higher mammals and lead optimization. So next, we still have many other amines from the parent structures that we found were metabolized in MTB, and we've really only started to study a subset of these amines, but we know that many of them are very structurally diverse, so we still have many other POA conjugates that have yet to be explored. And that's it. So I'd like to thank everyone in my lab, especially David and Pradeep, for just their phenomenal mentorship. Carly Levine, who preceded me in the lab and who trained me in BSL-3 and whose project I took over. Alyssa, Hassan, Nishant, Inchara, and Kaliswa for their work on this project. Preeti and Marizel for just the really intense job of making sure BSL-3 is running. And everyone else whose name I could not fit on here for just letting me stop by and chit-chat with you. I'd also like to thank our collaborators in the Freundlich Lab, Joel for helping us with the modeling, and Srinivas for helping us synthesize some of our PT260. The Zimmerman Lab, who, Matt and Fraught and everyone else who are just experts in pharmacokinetics and in LCMS. Jeremy Rock from the Rock Library for sharing his CRISPR library with us, and Drs. Bell, Syracusa, and Nidich for their guidance as part of on my thesis advisory committee, and Dr. Chan and Dr. Abramovich, who's joining us from Michigan today, I think, for being my readers on my dissertation committee. Pamini, John, and Myra for running the MD PhD program. Francesca, Audrey, Miracle, and Jennifer, who I bugged so last minute for grant submissions, and they still calm me down every time. And then my funding through NIA. Finally, I just have some pictures of the lab. Here's some rare photos in BSL-3. Usually everyone in the MD PhD program. And this is my favorite photo of John. I think he found a wand at our holiday party, and he was casting a spell on us to publish either Nature or science papers, I don't know, but we're all very excited for that magic to manifest, which we're eagerly awaiting. And yeah, and a special shout out to David and Pradeep really for helping me over these past few years. So, there was one time I asked David for time off, and I think he emailed me back saying, sure, but, just please don't come back with any lacerations, concussions, or heat stroke, which really departs from the typical response of, can you get me X, Y, and Z before you leave? And it just so happened that on that trip, there was an earthquake in the mountains where I was hiking. And I think David called me before my parents, just completely panicked. So he is now on my contact in case of natural disasters. He's great. And and then Pradeep, those of you who don't regularly have questions for Pradeep, you might not know this, but there is always a line outside his door. You have to wait. He is so patient with us and so kind. And he also makes sure that every student who leaves the lab gains the important skill of being able to look at this, see a full experiment, which I think I can now do. And with that, before I go on to the rest of the acknowledgements, I'll take some questions.
I'll let you answer the questions, but I just want to say, what a great talk, huh? Let's keep moving.
Ryan, then Armin.
I was kind of interested in what you were saying about the meta electron withdrawal numbers, increasing stability. Have you guys tried any of that with the JSF port 4302 or any of the others?
No, so we haven't tried that yet. I think part of our thought process in using this approach to code design is that we sort of avoided that initial medicinal chemistry by first generating all of these structures. And now that we're seeing these patterns, we can start to, with the help of Joel most likely, create these structures that have more of the characteristics that we want to see. So in this case, stability in mice or in a model organism where we can study these compounds more. So I've looked into what groups we can add there to make it more electron withdrawn, but we have not done that yet. It's fine.
So, with the mutation studies that showed what mutations led to resistance in your compound, I saw there was one gene that started with a P that showed up a number of times. Do you know what that gene does and why?
So that gene, so it's PSTS3, is involved in phosphate uptake and regulation. It has come up as a hit that pathway has come up as a hit in genes that can lead to PZA resistance in TNC studies, and then also Hassan Safi in our lab is studying that pathway, and he finds both acid resistance and comes up even more when you add PZA activity to acid. So we think levels of phosphate can affect PZA activity.
Someone monitoring the chat?
Yeah. Just lots of great jobs.
I had a quick question. So there was that one transcription factor, the RD whatever, that was had a different effect between the PZA and the novel drug.
Yeah.
Do you know what that transcription factor does or what kind of pathways it regulates?
Yeah. So sorry, I just realized people in the chat may not be able to hear the question. So the question was that there was the one gene that for which knockdown led to increased vulnerability in PZA but not PT260. There's a transcription factor. Do we know what it regulates? I started to look into that. I knew that it regulates the side genes in MTB, but I have not fully explored all the pathways that it's involved in.
Nothing else from the chat? Okay, well, thank you, everybody. If Swethas should pass her defense, there's a party scheduled later this afternoon.
Yes. I have a few more emotional photos to share. I'll be very quick. These are kind of going to be the hardest sides for me. And I might not be able to get through them, in which case I will just put them up. So, my dad and my sister passed away last year, but they both really wanted to go to grad school, so it feels a little unfair that I can be standing here and they can't, but I really think that I wouldn't be here without them, so I don't know, there's not much else to say on that. But to everyone else who just really carried me through this past year and years before that, I love you guys so much. I do not take your support for granted, and you guys just mean the world for me. I'm not going to go through every single photo here because there's a lot of you. But I did have to just make one side for Alyssa because I'm going to miss this girl so much, and everyone keeps telling me that when I go to med school I'll just be across the street, but it's not the same as being 20 feet away, and whoever I'm working with next year has really big shoes to fill. So, thank you. And now we're done. So, Dr. Abramovich, I know you're online. I think that we're going to move the closed session to a different room. So I will open up the Zoom link there, maybe in like 10 minutes or so. So maybe you can take a short break and come back.
Okay, sounds good. Great job.
Thank
See you
you.
then.
Thank you.
I brought everything at home. I don't know. I was gonna try to go do work while she was defending, but yeah. So many like techniques. Oh, a bag of cookies.
Picking up that intensive. Dig up the bulbs every single at the end of Yeah.
And then they pile them in a big hill. And
So
they're
you just
full.
grab the poles and then.
Yeah.
I think so. It's a short drive.
Interesting also like what we talked about, like you want to kind of kill the music when you're recording and then put something else in. Swethas!
To another doctor.
Then another doctor. QT260.
To QT260.
QT260. Because she's cute. 260 out of 250. Yeah.
Hopefully she passes.
And you can try again.
Yeah, oh come on.
Knock on wood.
Alex. Like after work. It was so much fun. It was the day after. Let's see if I can split my water.
It's a lot of B-roll.
Hey,
You gotta pour more in. Pour more in.
gotta have it.
I split the G.
Oh, me too. Now that's a draft.
What is that? My toot.
Yes.
I thought it was.
Oh yeah. AKA QT260.
I like that one.
Wait,
Stumble on
you
it.
spell out 260?
No.
Rhyme me some.
I think we should sing happy birthday. That would be.
Wait, let's just wait. Happy birthday to you. Happy birthday to you. Happy birthday, dear Swethas. Happy birthday to you. No. Pop it. Did you pass?
Yes.
Oh, that's so cool.
What a will.
Keep it short and sweet, you know? There's 100 other people here to see her. You're hogging up all the time.
I know, we're throwing them all.
Yeah.
There's no patient.
Unlike
Oh,
these.
yes. Please feel free to keep your fans.
Yes, they're waiting.
Second line, the second line. Yeah.
Ah, the good stuff.
Don't know this. Swethas did really well during her defense. I think that this is seriously one of the least number of revisions that were requested in any committee I've ever been on. They haven't wanted to do some very, very minor stuff. And then they told her if it's too hard, don't even do it. So that's pretty good, pretty damn good. I had someone stop me, one of the reviewers, Mark Sarcusa, who's very serious, as you know, stopped me and said that it was the kind of data that could be totally confusing, and you made it super clear. So I hope everyone understood it. It was really very, very clear. I understood it. It's really good. So there's actually some rules about alcohol in this place, which is you can't serve it without a permit. So we don't have alcohol. I did buy 3 champagnes. They're true champagnes, but they've just removed the alcohol, so they probably taste even better. We'll find out. I do want to be able to toast. Bought some cups here too. Should I have little comfortable partaking? There's also 1 egg-free cake that Buddy brought in.
Yeah, there's vegan
Cupcakes.
cupcakes.
Okay, that's great. So this is a really, really happy time for you. It's a very sad time for the rest of us. We're really glad for you, but we're also kind of weeping inside because we're really, really, really going to miss you. I'm going to miss you. I know we're all going to miss you. And don't make yourself scarce. We definitely want to, see you. Do you graduate this year with your PhD? Or have to wait until you get your
As long as I submit my dissertation by the 15th, then it's this year.
Okay, so we will see her again at another celebration where we can have real champagne.
Do you want?
Are you?
Yay!
Let me just try to serve. how many cups we need, but I'll just start pouring, so people just need to kind of, if someone could just let the cups out, and I'll just pour. And we can always.
No.
Okay. That's absolutely fine. Do you want to introduce your friends to us, since some of us don't know anyone?
Yeah. Well, since I don't have to, but no, I'll say a few words too. Thank you all so much for coming today. I've played around with the idea of thinking about going somewhere else for residency, and sorry, I'm just constantly crying these days. But you guys are like the biggest reason to stay in New York, and I'm just so lucky to have you guys as a support system. And I love you all dearly. That being said, most of this group right here is either from our lab or Queenie's lab or Joe's lab in our hallway. This group here is a mix of my college friends and my med school friends.
Woo!
And this group over there is we all climb together, so they literally saved my life. And Chris and Noel are also students here, and Carter. So yeah, just get to know each other, and don't be scared of each other.
What?
You want to say something?
Yes. Can someone else go first? I didn't think for me. I knew you.
Pradeep?
I'm not too good at speaking.
Speak up.
At times when people are leaving, so yeah, but Swethas, it has been great all this while. Just not beyond. You are very inspiring to other people around in the lab, so it has been really wonderful. And you know
Now listen. You have your own slide.
Swetha, over the time spent with you in this lab, you've truly become like family, and I know you'd say that I've been there for you, I do work for you, I show up for you, like, but truly, like, it's been such a gift having you in lab and in my life, and it's been a pleasure. I can't wait to see what's in store.
Oh.
Anybody else? Climbing friends?
Climbing friends.
We love you, Swethas.
Woo!
Every time. Cheers.
Yeah.
Cheers.
Yay.
We have those cups too. So what do your college friends think about her being a doctor before the rest of you?
Well, most of them are doctors.
Yeah.
Not either.
No, we have no hope of becoming doctors, so we're very proud.
We're very proud too. She's the smarter kind of doctor. So.
Does anyone have a funny story about Swetha?
Oh.
That's also appropriate.
Oh, I'm sure I do. Let me think.
Do you ever get I don't know, like a banana stuck in a carabiner halfway up a collar? Upside down?
Jumping in the bus.
Sort of.
I don't think I can do it.
Like the first time I met Swetha, it was in a car, and Jan introduced me over here. And sometime during our trip, her and another friend, Sean, we left them to their own devices. We set up like a top rope, and they were like, you guys got this. And me and Jan went off, and like half an hour later, we were like, where'd they go? Like I thought they'd be back by now. Like 40 minutes passed, 50 minutes passed, and then we were like, look at each other. like, you know, if they die, it's on us. Because it was their first time out there. Jan went for them, and it turns out that their rope did get stuck in the carabiner, and they were trying to figure out how to get it out.
We just left the knot in when we pulled it. Yeah.
Oh, jeez.
I'm very surprised.
I'm sure I have a lot of stories. I'm trying
Well, I
to
have
think
one
of one
question
that's not
for
too
you
many.
before you leave. Is it Sweta or
Okay, so.
where's Sweta?
So.
I should know this before you leave.
The confusion, I think, is that in North India, most people with my name pronounce their name Swetha, but my parents pronounce it Swetha. So I think when I came to lab, I was saying Swetha, but a lot of people in our lab were North Indian, so they would say Swetha, and it got too confusing. So I just but my parents say Swetha.
Okay.
Yes.
Finally, all these years.
Or Swety.
Or many other.
She calls me Toot. So Toot.
Yes.
Because you're very gassy.
And now I'm going to call her QT260. QT260 is my new name for her.
Oh, we'll say it a little bit.
QT260.
Oh,
like cutie.
QT260.
260. QT260.
So I really think that.
We were paying attention.
I really think that given Sweta's
Swetha.
value to all of us as a human being, even within a scientist, it would be good if I didn't give this toast, but someone else did, one of her friends. Someone has to give her a toast.
Alex, you're a good toaster.
I think we need more toast.
He's got the camera.
I will say to Swetha, who we hold so dearly and fondly in our hearts, and who I genuinely hope recognizes the impact that she's had on every one of us, the love that we feel for her and the love that we receive in response. And I hope you feel proud of yourself today, and I hope you feel all of the pride that is coming from us. And yes, I'm excited to see where you go, but I'm also really, really happy for every step that's brought you here. So, to Swetha. Doctor.
That was very nice.
Everyone should eat.
The key story isn't appropriate. Yes, the key story is really inappropriate.
This is cute. The keys isn't so bad. I guess the keys isn't really bad.
No, that's what you bought.
At least it's better than that.
No, it isn't.
Why? I disagree.
It's for Ella. I promised her a picture. Just put it like closer. There you go. Now you have to bend down a little bit and say hi, Oma. Nice.
Hold on. Okay, go.
The way that I knew you were here when I walked into the auditorium is I was like, there's a camcorder there that can only do one thing.
Woo! Okay, you can stop. You don't have to do that.
Oh, that's so pretty.
Yeah, do a
That's
couple of
celebrating this
slides,
lunch.
slides.
Oh my God.
But then he made them back to yeah, he got convinced. Me and then the headset are convinced. Yeah. I didn't know it like that. Like what?
Is it Dr. Sway?
Oh yes, great talk.
TRSK.
You couldn't think of a story, which is wild. I can only think of inappropriate stories.
I am
story too, but I thought, well,
Wow.
Right?
that is
great stuff.
Always these moments are like,
that was the
I should not say this one, but.
as well.
Are you familiar with that?
I don't have dance moves.
Oh, no, never do I. You're a pro. I looked at the,
I think
looked
overall
at the sign
it was
after we
good
were
that we
like
didn't do
walking in.
that.
I was like,
Because the cars are gone, so I thought,
yeah. They was my thing.
my car's right here. Oh, wonderful.
Well, yes, now it's on.
Oh, he's taking footage. He's doing crazy moves. He's camera. Oh, my penis is in the car. I gotta get my penis. You guys take it easy. Have fun in the big city.
It's been lovely meeting you.
Nice to meet you. So we gotta do this again.
For sure.
Yeah.
He's filming.
Yeah, I'm coming with you. I'm sorry, we get to do this again.
Yeah.
We're just gonna